Greetings everyone, welcome. This is our first math talk of this year, so that's very exciting, and I'm excited to kick it off with Dr. T. So in this very room, I took my first math class at Grand Rapids Community College, and Dr. T was my instructor. That was 2011. Oh, welcome, come in, find a spot, sit, please. So it is wonderful to have Dr. T here. I asked him the first year that he taught, and he told me 1964 was the first year that he taught mathematics. That was several years before I was born, and so that's very impressive. And then here at Grand Rapids Community College, taught as an adjunct on and off from the mid-90s until about 2016. So we've taught the complete repertoire of classes here, I think, too. So please join me in welcoming Dr. T, and to enhance our understanding of the harmonic series and series similar to that.
Good afternoon. I'm glad to be here again. I'd like to talk about subject which I thought long time after I have been retired. About series. First of all, how many did take math courses from you? Did all of you took math courses? Yes? Okay. How about calculus? How about calculus 2? Perfect. Perfect. So you, almost all of you, know what is a series. A series is a sum of an infinite number of terms. Yes? So let me speak. A series is an expression of the form A1 plus A2 plus A3 plus AN, or shorter, the summation sign from k equals 1 to infinity, A sub k, where the terms A sub k, so they are called terms, are numbers. So what does this mean? We have to assign a meaning of this expression because we don't know how to add an infinite number of terms. This is the problem. Here is the problem. We cannot add an infinite number. So, and the procedure is the following. S1 equals the first term in my sequence. S2 equals the sum of the first two. S3 equals the sum of the first three. And so on. Sn is the sum of the first n terms, and so on. So in this way, we found a sequence of so-called partial sum. So if this sequence is convergent, then we say that the series is convergent. And if the sequence is divergent, we don't assign any sum of our expression. We don't assign any number. So it is very normal to be so, because if the sequence of partial sum approaches a number, is convergent approaching a number, the larger is n, the more terms we add in the sequence. So it is normal to be so. And now, if we consider a convergent series, this means the sum of the partial sum sequence of partial sum is convergent. If we consider a convergent series, then what can we say? S sub n minus S sub n minus 1 is equal to A sub n. This, if we add n terms and we subtract the first n minus 1, then we get the term A sub n. Now, if we pass through the limit in this equality, Sn has a limit. Sn sub n minus 1 has a limit, the same limit. The same limit. And therefore, if we pass through the limit, this difference would be 0. So limit of A sub n, when n approaches infinity, of a convergent series is always 0. So we have found the first important theorem in our exposures here. So, and what is important is that if the series is convergent, the limit of the general term is 0, but the reciprocal is not true. There are series for which limit of A sub n is 0, and the series is divergent. And we will speak in a moment of this kind of series. If the terms of the series are positive, we speak about series with positive terms. These are important because when the A sub n are all positive, then the sequence of partial sums is increasing. And being increasing is enough to be bounded to be convergent. So therefore, for series with positive terms, we have a theorem of convergence A sub n and B sub n are terms, series with positive terms, such that A sub n is less than or equal to B sub n. Then the following statements are true. If the series B sub n is convergent, the series A sub n is convergent. If the series A sub n is divergent, the series B sub n is divergent. This is so-called a comparison test valid for series with positive terms. If the series, the terms of the series is one positive and one negative, alternates positive, negative, and so forth, that series is called an alternate series. And for alternate series, maybe you know that there is a test of convergence, very strong test of convergence, is called the Leibniz test. And the Leibniz test is the following. If the terms of an alternate series, the general term of an alternate series, basically not exactly the general term. Let's keep outside -1 to the n minus 1 the expression which gives you the alternating of the series. So if a sub n approaches 0, decreasing, then the series is convergent. This is the Leibniz test. Now, exactly how we spoke about series, I think is enough for series at this time. Exactly how we spoke for series, we can speak about infinite products. What is an infinite product? Is an expression of this kind. A sub 1 times a sub 2 times a sub 3 times da da da, a sub n, and so forth. Or shorter product from 1 to infinity, a sub n. Like in the situation of the series, we cannot multiply an infinite number of factors. This time are called factors. We cannot an infinite number of factors. So the procedure is similar to the series. We consider partial products. P sub 1 is a sub 1. P sub 2 is a sub 1 times a sub 2. P sub 3, a sub 1, a sub 2, a sub 3, and so forth. P sub n, a sub 1, a sub 2, a sub n. And stop. Yes, multiply the first n products of our sequence. And if the sequence P sub n is convergent, here is a catch to a non-zero limit. To a non-zero limit. Then we say that the infinite product is convergent. If P sub n is divergent, or the limit is 0, or between all these factors there is 1, 0, then the product is divergent. So, exactly as series, necessary but not sufficient condition to a product to be convergent is that its limit, the general the limit of a sub n, the general factor, to approach 1, this is the condition as necessary for an infinite product to be convergent. Here I will speak. Maybe many of you already know that there are several functions, very well-known function, which can be expanded in an infinite product. And these are the well-known function sine x, cosine x, hyperbolic sine x, hyperbolic cosine x. hyperbolic sine and hyperbolic cosine are not so well known for you, but sine and cosine should be known. And the hyperbolic sine, the expansion in the infinite product of sine x is this one, is the product from 1 to infinity of 1 minus x squared over k squared pi squared. And cosine x is product from 0 to infinity, 1 minus this expression. Why did I remind you this? Because these two expansions leads to two well-known expansions. Maybe you heard about Wallis formula. That guy lived in 1600, well before us. And he found that 2 over pi can be expanded in an infinite product as 1 times 3 over 2 times 2 times 3, 5, 4 times 4 times 5 times 7, 6. Here I made a mistake. 6 times 6. Here is. And so on, 2n minus 1 times 2n plus 1 over 2n times 2n, and so forth. Not only that, but also another unexpected expansion in an infinite product of square root of 2. I failed to tell you that for x equals pi over 2 in this, we find the Wallis formula. And for x equals pi over 4 in the expansion of cosine, we find the expansion of square root of 2 in an infinite product, which is this one from here. Okie dokie. Now, a short incursion in calculus and the harmonic series and other related series. First of all, the basic inequality in calculus is what is here. 1 over t plus 1 is less than natural logarithm 1 plus 1 over t, which is less than 1 over t. And here, in order to be a little bit interesting, I don't want to be, but the proof is very basic, and here is one of these proofs, one of many. Do you see? Here I consider the graph of the function 1 over x, and here is a with the coordinates t comma 0, b with the coordinates t plus 1 comma 0. T and t plus 1. B prime will be, what will the coordinates of b prime be? Will be the same, t plus 1 and 1 over t plus 1. And because this is parallel, the coordinates of A prime will be t and 1 over t plus 1. What will be the coordinates of A double prime and B double prime? A has the coordinate t, and because this is on the curve, is 1 over t. So A double prime has the coordinates t and 1 over t. B double prime has the coordinates t plus 1 and 1 over t. My apologies that I didn't include here the coordinates of those numbers. Now, A prime, B is a rectangle. What is the area of this rectangle? The area of the rectangle is the base, 1, times the height, 1 over t, is 1 over t. 1 over t plus 1, because BB prime is 1 over t plus 1, is this one. The area of A double prime, B double prime, B, the base is 1, and the height is 1 over t, is 1 over t times 1. And the area of this trapezoid A double prime, B prime, B, curved trapezoid, is, as very many of you know, is integral from t to t plus 1 of 1 over x dx. Is here. And this is the relation between the three areas. And now, because this is natural logarithm x, so we found that one over t plus 1 is less than natural logarithm 1 plus 1 over t. This is natural logarithm x between t plus 1 and t. This means natural logarithm t plus 1 minus natural logarithm t. Natural logarithm t plus 1 minus natural logarithm t is here. Now, the third property I will jump over the third property. The third property concerns the following two sequences: un, 1 plus 1 over 2 plus 1 over n minus natural logarithm n plus 1, and v sub n, 1 plus 1 over 2 plus 1 over n minus natural logarithm n. So these are very similar, only this one is natural logarithm n plus 1, this is natural logarithm n. These two sequences have the following properties. U sub n is increasing, v sub n is decreasing. V sub n minus the second, v sub n minus u sub m is greater than 0 always. So if you subtract a sequence from a term from here minus 1 from here, then you get always positive. And the third is that these two sequences are convergent, both of them towards one limit. This limit is called Euler constant, or by a mistake of the history, Euler-Mascheroni constant. Mascheroni constant. And the value of this constant is here. And do you know something? At this time, in 2022, we don't know if this number is rational or irrational. If you find out what is, then you gain fame and fortune. Fame because very many people try to do it, and fortune because the price is several millions of this proof. Okay. I will not stop to prove this property. I will go to the third property. Do you see? Here is some of the proof. The situation is this one. U1 is 1 minus natural logarithm is less than U2, is less than U3, is less than Un, is less than Vn, less than V2, V1, which is 1. So both these two sequences are between 1 minus natural logarithm 2 and 1, are squeezed between these two numbers. 1 minus natural logarithm 2. What is 1 minus natural logarithm? Let me find out here. 1 minus natural logarithm 2 is 0.306. So these two sequences are between 0.306 and 1. The last property, which is a little bit mysterious, is number 3. Do you have with you calculators? Do you have? So take some calculators with you. And each of you choose a number, a natural number. For example, 53, 74, 121, whatever number you want, okay? Choose that number. Let me choose one number. What number do you want me to choose? 36. What? 36. 36? So he told me 36. What I will do, I will evaluate natural logarithm 1 plus 1 over 36. What do you think is this one? Natural logarithm 1 plus 1 over 36, close the parenthesis, hit enter. What is 0.27, 0.27 and whatever. No significant number. Let's see a little bit more deeply if this number is not significant. Let's hit what is the inverse of this number. What is 1 over this one? So hit everybody x to the minus 1. Oh, yes. What is x to the minus 1? Is something interesting here? What is interesting? Do you see? The integer part of x to the minus 1 is exactly the number which that guy told me to choose. Is 36. How come is that possible? Is this only by chance, a chance or no? No, not at all. So try eventually more than that, and you will see that, yes. So, and the third property which I'd like to talk to you a little bit is referring to natural logarithm 1 plus 1 over n. Let me see, 1 plus 1 over n. How is this here? Yes. What is 1 plus 1 over n? And the property shows me that is 1 plus 1 over n plus lambda n, where lambda n is a number between 0 and 1. So, therefore, is exactly what I told you. The integer part of the inverse is n plus decimal part, lambda n. Is decimal because lambda n belongs between 0 and 1. And how is this possible? I will only talk to you a little bit faster about this. Is what I will do. I will choose the function f of x, 1 over x plus n, on the interval 0, 1. Here, the computer didn't write. Here is r, the real numbers. The printer didn't want to print this this letter. And what do we see? We see that what is f of 0? F of 0, what is f of 0? Is 1 over n. What is f of 1? Is 1 over n plus 1. So f of 0 and f of 1 is 1 over n and 1 over n plus 1. Now, you know that this is a continuous function. And any continuous function has the intermediate value property. So what is that intermediate value property? Takes any value between two given values. My given values are this one, 1 over n plus 1, and the other one is 1 over n. But f natural logarithm of 1 plus 1 over n plus 1, 1 plus 1 over n, this is a value between these two. So, therefore, it will exist a number between 0 and 1 such that the function takes exactly the value 1 over n plus that value, which is this. Now, this is the what I wanted to tell you about the series and properties related to this series. Now, I spoke so much about the harmonic series, and I didn't say what is that. The harmonic series is this one. This is the harmonic series. Sum from 1 to infinity, 1 over n. Now, probably, who knows, I don't know exactly, why this is called the harmonic series. Probably because if you take 3 for example, excuse me?
Use the on your table there. Those brand new ones marked.
I
Use these markers. These are brand new.
this?
Yeah,
Oh,
use those two. Those are brand new. Those are
okay. Thank you. If we take 3 consecutive terms, 1 over, let's say, n plus 7, the next one will be 1 over n plus 8. The next one will be 1 over n plus 9. I'm taking 3 consecutive terms of this series. Then these terms have the property. This one is the harmonic mean of these two. The harmonic mean of these two is this one. And probably that's why that one is called the harmonic series. Who knows? I guess this one is one explanation, one plausible explanation. This is one series. The other series, did I write the other series? No, I didn't write. The other series about which we'll talk is sum from 1 to infinity, natural logarithm 1 plus 1 over n. These are the 2 series about which we will spend our time from now on to the end. Both of them are divergent. let me show you that this one is divergent. Is a series with positive terms. So the partial sum is an increasing sequence. Let's show that is not bounded. What is 1 over 1 greater than natural logarithm 1 plus 1 over 1? Do you remember this is the first inequality which we wrote? Natural logarithm 1 plus 1 over 2 is less than 1 over 2. Natural logarithm 1 plus 1 over 3 is less than 1 over 3. And so on. Natural logarithm 1 plus 1 over n is less than 1 over 1 plus 1 over 2 plus 1 over n. If we add these together, what do we have? Natural logarithm 1 plus 1 over 1 plus natural logarithm 1 plus 1 over 2 plus plus natural logarithm 1 plus 1 over n is less than, this is called Hn, the harmonical, the partial sum of harmonical series of order n. But what is this? This is natural logarithm 2 over 1 times, this is 3 over 2 times 4 over 3 times n plus 1 over n. Do you see? 2 cancelled out with 2, 3 with 3, 4 with 4, n with the previous. And here remains natural logarithm n plus 1 is less than h sub n. But natural logarithm n plus 1, when n approaches infinity, approaches infinity. Yes, you know that natural logarithm is an unbounded function. If this one approaches infinity, of course this, which is larger than that, approaches infinity as well. This is 1. Now, if you look into the reference, you will see the reference number 5, Havil, the gamma function, is an excellent book. It is an excellent book. And that guy gave some values. What is H2? H2, do you know what is H2? Is 1 plus 1 over 2, is 3 halves. H3 is 1 plus 1 over 2 plus 1 over 3, is 3 halves plus 1/3, 3 halves plus 1/3. Oh, is difficult, but is manageable, yes? And the guy told us that H100, so if you add 100 terms from the first series, you get barely 5.187. If you add 1,000 terms, you get 7.486. 1,000,014. So therefore, the series is very slowly approaching who knows what. And here I showed that the partial sum of the harmonic series are not bounded, so therefore the harmonic series is divergent. Now, people during the history tried to chop off portion of those terms of the harmonic series to see if we get something convergent. If we consider only 1/2 plus 1/4 plus 1/6 only with the denominator even numbers, no, we don't do anything because the series remains divergent. Any attempt to chop some of those terms off from the series is not, doesn't lead to a convergent series. But what is interesting is that in 1914, this guy, Kemper, devised one method to get a convergent series. To eliminate from this series all terms which has a given digit in the denominator. And I got the number 3, for example, here. Eliminate from the series all terms which get 3 in the denominator. Then the denominator range from 1 to 9, what terms are admissible is 1, 1/2, 1/3 is not, 1/4, 1/5, 1/6, 7, 8, 9. How many? How many? 8. How about from 10 to 99 range? 10, 11, 12, 13 is not because it has 3, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 not, and so forth. Up to 30. So from 30 to 39, neither one is acceptable, and so forth. You will get 8 times 9 acceptable terms, denominators. From 100 to 999, 8 times 9 times 9, which is 8 times 9 squared. And so forth. This is the rule. Now, let's try to find an lower limit of the sum. From 1 to 9, what is the highest number? 1 over 1, 1 over 2, 1 over 3. 1 over 1 is the highest. Upper bound. How about between 10 and 99. What is the highest? High. Is 1 over 10, because 1 over 11, 1 over 12 are lower. So this is, and so forth. These are the lowest, the upper bounds of the sum of the terms. Now, if we add all this, eight times 1, 8 times 9 over 10. 8 times 9 over 10 squared. 8 times 9 over 10 cubed, and so forth. And go on from this. With this is a geometric series. If you factor out 8, the ratio of the series is 9 over 10, and you get out to 80. So, therefore, how is the sum of these two? An upper bound of the sum is 80. Is much larger than expected, but it will do it. So the series, the sum of the partial, the sequence of the partial sum is bounded, has an upper bound by 80, is an increasing sequence and has an upper bound by 80. So therefore the series is convergent, because the sequence is increasing and has an upper bound. So the series with 3 missing from the denominator is convergent. The series with 4 missing in the denominator is the conclusion is the same, is increasing. So therefore any digit, how many digits are there? 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yes? These 9 series are all convergent. And this one also is convergent. This is for series with positive terms, chopping out some denominators. Now, okay, what I will do now, I will show you something which I think will be enough for you. These two series are divergent, both of them. How about their difference? How is sum from 1 to infinity 1 over n minus natural logarithm 1 plus 1 over n? How is this series? I will show you that this is convergent. And this is convergent towards a very nice number. First of all, how are all these numbers? Do you remember the first inequality which I proved to you? How is 1 over n compared with this one? 1 over n is greater than this one. Do you remember? So therefore this quantity here is positive. So therefore I should it will remain to me only to show that this is bounded. Let me do it. What is 1 over 1 minus natural logarithm 1 plus 1 over 1 plus 1 over 2 minus natural logarithm 1 plus 1 over 2 plus 1 over 3 minus natural logarithm 1 plus 1 over 3. And generally, 1 over n minus natural logarithm 1 plus 1 over n equals. Now, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over n, this is h sub n minus. Do you remember I evaluated previously this one plus this one plus this one plus this one? Do you remember what was it? What was it? What was natural logarithm 1 plus 1 over 1 plus natural logarithm 1 plus 1 over 2 plus natural logarithm 1 plus 1 over 3 plus natural logarithm 1 plus 1 over n. Is natural logarithm 2 over 1 times 3 over 2 times 4 over 3 times n plus 1 over n. 2 with 2 cancel, 3 with 3 cancel, 4 with... So is natural logarithm n plus 1. So this is h sub n minus natural logarithm n plus 1. But what is this one? If you look back in the property number 2, look back to the property number 2. This is what? This is exactly u sub n. Do you see that? And what is the property? In the property number 2, we proved that u sub n approaches to gamma. So therefore, what is the nth partial sum of this series? Is u sub n, and u sub n approaches to gamma, so this sequence, this series is gamma. So we proved that sum from 1 to infinity, 1 over n minus natural logarithm 1 plus 1 over n is gamma. Let's stop with the following stuff. Let me write here, instead of natural logarithm 1 over n, let me write natural logarithm e to the 1 over n will be the same. Do you agree with me? So let me write again gamma equals sum natural logarithm e to the 1 over n, and minus natural logarithm is over 1 plus 1 over n. Do you agree with me? And from here, taking the natural logarithm outside. Here instead of sum, I got what? What do I get instead of sum? What is the sum of a natural logarithm? What is natural logarithm? Something plus natural logarithm. Something else plus natural logarithm. What is that? Is natural logarithm of the product. So the sum is changed into a product. So gamma is natural logarithm of the product from 1 to infinity e to the 1 over n over 1 plus 1 over n. And eliminating the natural logarithm, e to the gamma is the product from 1 to infinity e to the 1 over n over 1 plus 1 over n, which is a stuff from the gamma function. Did you hear about gamma function? Gamma function is called Euler large gamma of x. Is the expansion of the factorial to real numbers. Is something very special. Is something in the high math domain. So, thank you for your attention. Hopefully I didn't keep you too confused, or what I should say. If you have questions. Yes. Let me sit down a little bit. If you have questions. Yes. Yes.
You mentioned quite a while ago Euler-Mascheroni constant.
Excuse me?
The Euler-Mascheroni or Mascheroni constant?
Mascheroni constant.
Mascheroni constant.
Yes.
And you mentioned that historically that was a mistake to include Mascheroni. Why is that?
Because that guy was trying. What happened in history? I don't recall the name of the previous guy. Evaluated the Euler constant with, if I'm right, 25 or close to 30 digits. And Mascheroni, this Italian, tried to do better. But he was mistaken. The 16 or 17 digit was mistaken. So therefore, his work in trying to find the value of gamma was not accurate. So he has other results in geometry especially, but here he didn't, he was failing. But do you see how is the history? History attribute Mascheroni gave the name of the constant gamma. He said this is gamma because Euler said previously, probably 70 or 80 years previously, gave to this constant the name C. And Mascheroni said, no, let's call it gamma. And gamma was. So, yes, that's why is John, I
was familiar with the name, I didn't know how to pronounce it. But I was just curious, that's quite interesting.
yes, this was the reason for which I said that is
I was just curious if it had anything to do with your love of Euler.
excuse me,
I was just wondering if it had anything to do with your love of Euler.
with what?
You are known, at least by me, and maybe a few others, you are known to be very passionate about Euler.
Yes.
Yes.
Euler was, how should I say,
Just say what's on your mind.
the genius between geniuses was I think was up to this point the best mathematician the world have ever had. But like other people, they consider some, no, not consider, they think that Euler, not Euler, Gauss is somehow greater than Euler. I would disagree with that, but only in, so to speak, academic terms, but because I have no knowledge large enough to evaluate one or the other to their true value, because both of them and all mathematicians of the 18th century and 19th century were so great that it is no comparison. Okay. Thank you, sir. Thank you.
Thank you very much.